Director of the Institute, Shafi Goldwasser. I'll just say a few words of introduction and then we'll have the main act. So we have been here since 2013, and we are an institute for collaboration in theoretical computer science and adjoining fields. And in particular, the topics of this workshop, both the lattice part of it and the quantum part, which is the beginning, which Scott is going to start, were two programs that started right at the semester when the pandemic hit, and we left at sort of a week into March. And it was a wonderful program that continued also online. But what we decided is to bring people back this summer for an extended reunion, sort of 5 weeks. And this is the workshop that's combining both the lattice and the quantum sort of group. And we're extremely excited to having a very interesting program. Umesh is going to talk a little bit more about the program. I just wanted to say something that I think Umesh will reiterate, and that is that there are speakers that are not going to talk if people are not fully masked. You can, according to Berkeley rules, be masked or not. In consideration of the fact that we won't have those speakers here, and in general, if you could mask, we would appreciate it. We have extra masks here in the Umesh has a packet. There you go, Umesh.
Thanks, Shafi. So yeah, welcome definitely everybody to this workshop. It's I think that it was of course extremely unfortunate that we had to interrupt our 2020 program halfway through, but there were one can always look on the bright side of things, and the
What's that?
Yeah, what is that? So the bright side is that the two programs we had, quantum and lattices, already in 2020 there were ties between the two. People were communicating across, but in 2020 I think there was this sense on each side that people really wanted to learn about the other. They were very curious. They really needed, they knew that there were lots of interesting things going on in terms of that they needed to understand about the other. I think those ties have become just so much deeper now. And so in a sense, if we were to do it again, maybe we would not have wished for a pandemic, but we would have said, the ideal way to do this program is do half a semester now and then do another half semester 2 years later, have some sort of entanglement time, over time. And so in that sense, there's a positive side to it all anyway. Okay, so I think that's also something that's reflected in the program of this for this workshop. It's a week-long workshop with a quantum side and a lattice side, and then there's I think there's definitely an intersection in both halves, and then there's a very explicit intersection on Wednesday, when which is really deeply enmeshed, the two sides, the crypto side, quantum side. So I think it should be a very interesting workshop. Now there's another aspect of it which I should say that we have really tried to emphasize in this workshop because we've been so used to working online and in hybrid modes, and this is really a time for everybody to be together and in person. And so we've tried to keep this particular workshop to be in person, so that of course the workshop is much more than just the talks. It's also all the discussions you have around the talks in person. So that's why we've tried to make it absolutely everybody in person. And so as Shafi mentioned, there are speakers who for reasons of having family who are vulnerable don't feel comfortable speaking if people are not masked, and I can see everybody is. So thank you for doing that, and I don't think we have to go to the fallback mode there, right? So we'll try to keep everything in person. So we are starting off with this morning session on quantum algorithms, and there are two fantastic talks. by Scott Aaronson and Mark Zandry. So Scott will speak about so there's this subject which I think is really very both important and very interesting, which has to do with quantum advantage. So we've had these developments starting with Google's much publicized experiment or breakthrough on quantum supremacy, and then various events after that trying to show either to increase the number of qubits or to show that in fact though you can have classical algorithms that can catch up with duplicate the same results. And these have been I guess within the last couple of months there was another breakthrough showing that that classical algorithms actually can do rather well on random circuit sampling. So Scott's going to help us understand all of this. So really looking forward to it, Scott.
Okay, well, thanks so much for it's great to finally be participating in the spring 2020 Simons program. And yeah, it does feel like years of progress have been made during this program, right? So thank you for the introduction. Umesh actually gave me this title, like recent progress in quantum advantage. And then I had to think about, has there been recent progress in quantum advantage? And then I said, well, definitely, there's been this breakthrough by Yamakawa and Zandry, but wait, but that's the talk that's right after mine. So I'm going to try to give a overview of a particular kind of thing that I really want. Okay, so this talk is less to sort of present results than to sort of ask for something as clearly as possible. But by the way, I don't know if any of you have been playing around with DALL-E, the AI image generator, but when I asked it, like, how much structure do you need for huge quantum speedups? These were its answers. I'm not sure. I'm not sure if there's any insight in that or not. Okay, but okay. So my starting point is this. I think of quantum speedup as sort of a resource that we've been handed that is in some ways weirder than any science fiction writer would have had the imagination to invent. I think if you were writing a science fiction story, if you were going to have any kind of computational superpower at all, you would just make the halting problem easy, or you would make NP complete problems easy by just, some, magic, try every possible answer in parallel. And, and to this day, the misimpression persists that is what quantum computing is about. Okay, but we all know that it is something stranger than that. It is this complexity class BQP, which fits into the classical complexity classes in a somewhat weird way that we're still trying to understand in detail. Okay, and enough that we can do certain specific problems that are not known or believed to be in P. But as far as we know, not the NP complete problems. Okay, and even among the NP intermediate problems, maybe only some of them and not others. And yet, maybe also some problems that are not even in NP. Okay, so so what I would like to call the hammer of hype. So like when I every few days like some reporter is doing some quantum computing story and they're asking me like can I explain quantum computing in 1 minute, and I'm saying, well, can I at least have 5 minutes, right? And and the main points that I try to get across are, number one, it is not enough to just put quantum on top of whatever you want to do and create a superposition over all the answers. The only hope of getting a speed up quantumly is to exploit interference, right? Is to exploit the way that amplitudes being complex numbers are different from probabilities. You have to somehow set things up so that for each wrong answer, the contributions to its amplitude will cancel each other out. And for the right answers, the contributions to their amplitudes will be in phase and will add up. Okay, and what's non-trivial is that you have to do this even though you yourself don't know in advance which answer is the right one, right? Or else what would be the point? Okay, and of course you have to do it faster than any classical algorithm could have done the same thing. Okay, and this is the second central point. That you know, it's not enough to just get a quantum speed up compared to the first brute force classical algorithm you think of. The classical side gets to fight back, right? And and this is not just like sort of an intellectual point, but it is increasingly a practical point. Okay, as people are making concrete claims of quantum advantage for particular problems, we have to see whether they are actually beating what can be done classically. Okay, so now I'm gonna. This is sort of the most important slide in the whole talk. In fact, I could, if you get nothing else, I could probably just show you this slide and then stop. Okay, but so there are different so in this talk I'm going to be interested, first of all, in exponential speedups that we can get via a quantum computer. Of course, not all speedups are exponential. There is the square root speedup of Grover's algorithm, for example, which is also extremely interesting. If you run the numbers, the point where a square root Grover speedup would actually give you an advantage looks to be extremely far in the future. Okay, and this is because to run Grover's algorithm, you would need a fault-tolerant quantum computer, right? And so then you're paying an overhead of millions probably just to do that, and then the square root has to win over that, right? And so then your problem size might have to be in the quadrillions or something before there's an advantage. Okay, so I am interested in quantum speedups that we can actually demonstrate, in the relatively near term. Okay, so of course, there are already experiments that are trying to do this. They're and that's been a very exciting development over the past 2 or 3 years. These sampling-based quantum supremacy experiments. Okay, and we're going to talk about them. Okay, but we're also going to talk about how they have some very significant drawbacks. Okay, that we'd like to overcome. Okay, so if we want an exponential speed up from a quantum computer, like what is it that we want from it? And the way I think about it is that sort of there are 3 main properties that we want all at once. Okay, now I should say in the background, whatever we're doing should be efficiently doable by a quantum computer. Right, that is just assumed that's just obvious. Okay, but now in addition to that, okay, there are 3 additional things. Okay, the first is what I'll call NISQable. Okay, so NISQ was a term coined by John Preskill 5 years ago. It stands for noisy intermediate scale quantum. Okay, and basically it means can we actually do it with devices that we will plausibly have, let's say, over the next, either today or in the next 5 years, without needing to build a full, scalable, fault-tolerant quantum computer. Okay, so this is not a formal mathematical concept. We should be clear, right? It's a sort of thing where you know it when you see it. Right, but basically anything that involves sort of doing cryptography, on superpositions of inputs is, unfortunately looks pretty far from what we can implement today, right? What we can do today is typically, you can either with superconducting qubits, with trapped ions, with photonics, you can deal with, maybe on the order of 100 qubits. 50, 100, maybe soon 200. Okay, you can have some programmability in them. Okay, but you are, each 2-qubit gate that you apply, imagine that it has a fidelity of 99.5%, today, maybe soon it will be 99.9%, right? And that's, compared to what things were when I was a student here in Berkeley 20 years ago, right? That's astoundingly good. Okay, but compared to what you need to do fault tolerance, that's still not there, right? If each gate I apply has 99.9% fidelity, then I can only apply 1,000 gates, until there's a good chance of an error somewhere. Okay, so in the quantum supremacy experiments that Google and that USTC in China, have done with superconducting qubits, the depth of the circuit is about 20. Okay, so they do, 50 something qubits, about 20 layers of gates. Okay, these are the kinds of numbers to think of, right? And so, what can you do with 50, 100 qubits? Well, let's be generous. Let's say, 100 layers of gates, right? Well, you could apply a bunch of random gates, okay? And you can measure and you can see what comes out. Maybe you can do something more interesting than that, okay? But doing modular arithmetic, doing lattice computations, yeah, it's probably not going to happen. Okay, so until you can get fault tolerance, or at least some amount of fault tolerance. Okay, now second thing that we want, kind of an obvious one, we want to actually beat a classical computer, right? We want whatever task we're doing to be ideally exponentially harder for a classical computer. Okay, but this is, when you actually zoom in, this is often debatable, right? Often, sometimes you have a heuristic algorithm, you don't really know, what is the what's the quantum versus classical performance, right? If you squint, maybe there's an exponential speed up, maybe there isn't. So, we can say, there are speed ups that we can be more or less confident about, right? And I would like to be as confident as possible in the reality of the speed up, right? Ideally, I would like to have like two kinds of evidence together. I would like some formal hardness reduction. I would like some kind of formal evidence that the problem is hard. And also I would like, for the particular instance size that we're looking at, that people have actually tried experimentally to spoof it, with classical computers, and and there remains a gap in performance of orders of magnitude. Okay, so now the third requirement is one that has, I think really come to the fore over the past few years, with the quantum supremacy experiments. And this is, we would like to solve a problem where we can actually recognize a correct answer when we see one. Okay, when the device produces one. Okay, so this could mean the simplest way to achieve that is by solving a problem that's in NP, such as factoring or discrete log. Okay, but we can imagine broader ways than that to get verifiability. For example, you might achieve verifiability via an interactive protocol, with the quantum computer playing the part of the prover. Okay, and there's been a lot of exciting recent progress on how to do that. Okay, or if you're doing a quantum simulation, or a simulation of some chemical or some material, it might not be an NP problem, but you might be able to verify the answer by comparing against nature, by comparing against the chemical itself. Okay, so and validate the result that way. Okay, but if the verification itself takes exponential time, then that inherently limits the scale at which we can be demonstrating a quantum advantage, right? So we're now in the very, very interesting situation in the field that I would say that we know how to achieve any two of these three requirements. Okay, so what have the quantum supremacy experiments of the past couple of years done? They have gotten these two. They're we are doing them today in the NISQ era, and well, this I'm going to be generous, and I'm going to say, at least if you could do it with a good enough fidelity, then, the theoretical versions of these problems, I would say, would solidly beat, classical computing. The actual implementations, that's much more of a question. Okay, so, for simulating, let's say, solving the abstract boson sampling or random circuit sampling problems, right? We are pretty confident that that you will need exponential time to do that. Now anything you can do in the NISQ era, right? You have to worry about noise in your device, and then you're so maybe I should have sort of put this a little bit, trying to get into here, but at least a hope of going into there. Yeah.
Isn't that a really important point? At this point, somebody could say, actually, we do not know whether there's anything we can do in NISQ which solidly beats quantum, and that's really a serious open question given recent developments.
Yeah, I would say that. So let's talk about the situation right now. So there have been classical spoofing attacks, that have been published for both the random circuit sampling and the boson sampling. I would say that that a quantum advantage remains depending on how you define it. Okay, so I would say if you use enough classical cores in parallel, and you use tensor network methods, then you can simulate what these 53 qubit experiments, for example, but you are using, in some sense, many more cycles than the quantum computer is using, right? And so, as judged by time, you can achieve parity if you'll spend enough money for cores, as judged by carbon footprint, ironically, the quantum computer is winning, even though it needs a dilution refrigerator. So, but I would say that to really, sort of merit this being here, the most important thing to do, it would be to do these experiments with a better circuit fidelity, so if you can do, for example, if you could do the gates with 99.9% fidelity instead of 99.5%, then you can do a much higher circuit depth. When you do higher circuit depth, then the tensor network methods start struggling a lot more. Right. So this is, so quantum supremacy is still like, we are still in the era where, you could have an argument back and forth about it. It's, I think I sometimes use the analogy of like, Kasparov and Deep Blue in 1996, right? It is the, it seems to me that if you could, do these experiments, with a higher fidelity, then even with 60 qubits or so, we would not know how to use tensor network methods. So I'm being generous here, and I'm granting that the experimentalists are going to improve the hardware in that way in the next couple of years. Okay, but even the point I wanted to make was that even then we still have an issue with verifiability. Okay, so I would say that the deeper issue, the sort of deeper problem with the sampling-based quantum supremacy experiments is that we are inherently limited in how far we can scale them. Okay, and the reason is that the way that we verify these experiments is just by doing a brute force classical computation. Okay, we do a we take, so we literally just apply a random sequence of gates, let's say, measure, that gives you a sample from some distribution over n-bit strings. So, and then you keep doing that over and over, you get a bunch of independent samples, and then you have to, this is the hard part, you have to validate those samples somehow with your classical computer. Okay, and the only way that we know how to do that is something like this linear cross entropy benchmark, that Google has used, which says you just use your knowledge of the circuit, you calculate the probability that each of the observed samples would have been generated, by a correct circuit, and you sum them all up, and you see whether that sum is sort of interestingly large. If it's a real, if the quantum computer was working right, then you should be likelier to observe the samples that were predicted to have higher probabilities, right? So you can do a statistical test that way. Okay, and this is as far as we've given some theoretical evidence that it should be hard to spoof this, meaning there's the the current situation is that there seems to be there are polynomial time classical algorithms that can get an advantage in this cross entropy benchmark that goes like 1 over exponential in the depth, right? And this is the depth of the circuit. Okay, this is recent work by Boaz Barak et al. Okay, 1 over exponential in the depth, that's if the depth is 20, or let's be more optimistic, if the depth is 50 or something, then hopefully the experiment will be able to do better than that, right? And then we have something, we have a score that is hard to spoof classically, right? Or plausibly hard to spoof classically. Okay, but the biggest problem is that even to calculate this score, to validate the outputs of these circuits, we have to do this exponential time classical computation, right? And so that's why you're inherently limited. Okay, so these experiments have only gone up to as I said, about 60 qubits. Okay, but even if you were to scale them to 200 qubits and have it work perfectly, you could never prove it, right? Because not even Google can do a 2 to the 200 computation. Okay. And interestingly, even if you had another quantum computer, we still wouldn't know how to use that to validate it. Okay, because all the quantum computer can do is sample, right? And whereas what you need to do is estimate the ideal probabilities for these specific samples.
Okay. Scott,
yes.
Why can't you get around of the verifiability by just extrapolating from small instances, plotting on a log scale, and trying to see how things?
Well, that's exactly what people do. Right, you can just plot things on a log scale and just say, well, I believe it's going to extrapolate. That's exactly what is done, right? But then, then Gil Kalai has his opening, right? And he says, well, then, clearly the demon is, is going to come in at 70 qubits, right? Clearly, this is all going to stop working at the point beyond, just beyond where you've tested it. Right. So, you would like to be able to, directly refute that. Right. So, yeah.
There's a serious issue there, right? Which is once one talks about NISQ and so much depth, so many qubits, and then you really have to go to fidelities that are much higher, and by the time you get there, it's not clear that you're not in the regime for interactive verification already.
Well, okay, so there's a question here, right? I mean, as I said, NISQ is not a mathematically well-defined concept, right? Yeah. And it could be that well, one could argue the view that once one has a NISQ speedup that is just so solid that no one can question it, that at that point you are good enough that you can either do an interactive protocol, or for that matter, just a full fault-tolerant quantum computation, right? I don't know if that's an optimistic view or a pessimistic view, right?
That's one of the reasons it seemed to me that we are poised at a very interesting spot, where actually theory has a lot to say, and understanding these trade-offs is really important.
Yeah, no, absolutely. Okay, so I wanted to just briefly mention, so the other intersections here. Okay, so now, if you want sort of something in the NISQ era, that is in NP, right, that, clearly has efficient verification, there are, all these things that have been talked about a lot over the last decade, like the QAOA, which is quantum approximate optimization algorithm, which Ed Farhi and his collaborators have been studying, and which is sort of like a low depth variant of the adiabatic algorithm. So it's a heuristic algorithm for trying to solve optimization problems, and its main early selling point was that you could run it on a NISQ device, right? Because of the low depth, you could just implement it and see what happens. There are now hundreds and hundreds of papers, analyzing this algorithm. And yet I would say that none of them have sort of clearly established a case where, we could say, we believe that it is going to beat a classical, classical optimization methods. In fact, there were, there were candidates for that were then refuted. Okay, where classical approximation algorithms were found that can match or beat the performance of QAOA. Okay, so I think the best that we can say is that, well, we can't rule out that there will be some NISQ speed up here. It is worth trying it to see, right? And I would say something similar about NISQ algorithms for quantum machine learning problems. Okay, so okay, and then if we just give up on on NISQ and we just say well, assume a full fault tolerant quantum computer with as many millions of qubits as we want, but we want an exponential speed up, we want it to be efficiently verifiable, then of course, well, there's Shor's algorithm, in all of its many variations. There are the interactive protocols, famously, that of Ermila Mahadev, the subsequent work building on that. There is the new breakthrough by Yamakawa-Zandry, which you're going to hear about very shortly. Well, I'll mention something about it in this talk, which gives actually a new type of apparent exponential quantum speed up. Okay, and then there are simulations of quantum physics and chemistry. Okay, so here there's kind of a good amount, but we don't. I wouldn't say that we really know how to do any of this with a near-term device. So basically, we want to get into the center of this diagram, and clearly, there are three different lines of attack that you can envision, right? Number one, start with these, QAOA type, these sort of heuristic type of things, which is also what D-Wave and what, many other quantum computing startups nowadays, what their entire business models are based on, right? But, try to find something where you're actually solidly beating a classical computer, in a fair comparison. Okay, second direction would be start with, the verifiable speedups that we're confident about and find some way to shoehorn them into a NISQ device. Find some way, if you can even just reduce it from, thousands of qubits to hundreds of qubits, if you don't need some full error correction, but maybe some error mitigation, maybe you could, just barely get such a thing to work in the NISQ era. Okay, and then the third approach would be start with the kinds of quantum supremacy experiments that have been done, or that people are doing today, and then figure out a way to modify them so that the results can be efficiently checked with a classical computer. Okay, so all three of these approaches are being tried by different groups of people. I should say, another complication here is that sometimes even when we have a speed up that we're confident about, it might only be in the black box setting. Okay, and so there might be an oracle that we then have to figure out, can we instantiate it by a real function, in some way that preserves the quantum speed up. Okay, so that's sort of yet another axis here. All right, so let me just say a little bit, briefly about these different directions, from which you can try to approach the center of this diagram. Okay, so you can start with the sort of heuristic optimization methods and then look for big speed ups with them. Okay, and there was actually some very exciting recent progress on this. So the maybe the earliest quantum heuristic algorithm was the adiabatic algorithm of Farhi and his collaborators from the late 90s. You can think of it as sort of a potentially quantum enhanced version of simulated annealing, right? And we knew, even from like 2002 or so, that there are, you can construct fitness landscapes where simulated annealing will get stuck at some local optimum for exponential time, but the adiabatic algorithm will reach the global minimum in polynomial time by tunneling, out of the local minimum. Okay, unfortunately, for those fitness landscapes, once you knew what it looked like, there was there's a different classical algorithm that is, that will also find the global minimum quickly, right? And so I, for years and years, I gave out the problem: can you show that there is a black box, fitness landscape where the adiabatic algorithm will just provably beat any classical algorithm, in inquiry complexity, by a super polynomial amount. So that, during this pandemic has finally been achieved, first by Matt Hastings, who gave an n versus n to the log n type of a speed up, and then Gillian and Vazirani sharpened it to an exponential speed up. Okay. However, this is I took this diagram from the Gillian and Vazirani paper. It is it's for extremely bizarre, specially constructed fitness landscapes that I would have no idea how to realize them, in the non-black box world, let alone in any sort of practical problem, let alone in anything that we could fit onto a NISQ device. Okay, but that's the situation with the adiabatic algorithm. Like you can try it, in the NISQ era, but are you going to get a speed up? Who knows, right? Right now it's the whole thing is extremely empirical, right? You just you've got to compare against the best classical optimizers and try to squint at it and see what happens. Okay, there's also quantum, or even earlier than that, there were quantum walk algorithms where, again, for some very, very specially constructed graphs, you can get it so that a quantum walk will reach a particular vertex, in this case the exit vertex of this graph, provably exponentially faster than any classical algorithm, that can only access this graph as a black box. Okay, but this is for very special graphs. In this case, this is just two complete binary trees that are connected by a random cycle. This was the famous example of Childs et al. From 20 years ago. And, for more natural graphs, we have no idea, like, will this phenomenon generalize, right? Will there, for sort of typical graphs, will you get anything more than a Grover speed up? We don't really know. And as I said, for QAOA, even in the black box setting, we don't really have a candidate there for where is it going to give an exponential speed up. Okay, so that's the problem with these things. Okay, so now approach number two was to start with verifiable quantum speedups and then somehow make them NISQ. Figure out ways to implement them, without needing a full fault-tolerant quantum computer. Okay, so of course, we could start here with the whole family of algorithms that derives from Shor's algorithm. Okay, so factoring, discrete log, all sorts of problems involving abelian groups, such as elliptic curve groups, and then some very limited generalizations to non-abelian groups. And, I wish that I could, give, approximate shortest vector, on this list. But, we're still working on that, right? Or people are still working on, to what extent can we solve lattice problems in quantum polynomial time? And I'm sure that we'll hear a lot more about that this week. And then, the other big example here would be the simulation of quantum physics and chemistry. Hamiltonian simulations simulating the rates of chemical reactions, learning the properties of the ground states of various materials. Okay, so my basic feeling about it is that absent some breakthrough, all of this stuff seems to require fault tolerance. Okay, because it all seems to require representing numbers in binary, doing operations on them and superposition like modular exponentiation. We really need some new idea, I think, to figure out how to do any of that in the NISQ era. For quantum simulation, this is maybe the best shot that we have, right, of doing something in the NISQ era that is sort of actually, useful to someone and that, not unrelatedly is verifiable. Okay.
Again, in what sense
excuse me?
Can you say again in what sense these simulations are verifiable?
Yes, they're verifiable because you can compare against the actual molecule in nature. It's validated.
I'm confident that my model is a good model.
Yeah, exactly. So for example, if you're trying to, do a quantum computation of the rate of a chemical reaction, you can measure against, the actual observed rate of that reaction and, see if you get to chemical accuracy or whatever, right? So, so then even if the problem is not an NP, in some sense, you can use nature as an oracle. Right. So, now, unfortunately, people have calculated in great detail over the last 5 or 6 years, exactly what resources, are you going to need to do interesting quantum simulations using the known methods for Hamiltonian simulation and so forth. And, it used to be, formally polynomial, but just wildly impractical. Okay, and today I would say it's still impractical, but less wildly so. Right? Yes.
So there's an issue there, which maybe you can speak to.
All right.
Which is, there's dynamics where verifiability it's more clear how you verify it versus finding ground states where you get it to, in terms of provable or something, it's
well, you always need some observable that you're going to be measured, right? You always need, you don't get explicit access to the whole wave function, when you put a simulation on a quantum computer, right? So you always have to measure something, right? That will tell you something of interest, whether it's the magnetic susceptibility of your material, whether it's the rate of the chemical reaction, right?
I meant more that, if you're looking for a ground state,
Yes.
then there are questions about, how do you actually find that ground state? Isn't that a heuristic then? So finding a ground state in general is a QMA complete problem, right? And so we don't expect that in the worst case, even nature itself could do that, right? Now in practice, typically ground states are easier to find, and they're easier to find not just quantumly, but also classically. Right. So, you could say what I've been told, at least by the people who work on this, is that it seems like the better bet is to look at dynamical problems, right? To look at simulations of quantum dynamics, such as chemical reactions, for example. And so, estimates, for example, from the group at Microsoft have said that, with just, 100 or 200 qubits, you could already start learning things about, some, even like some industrially relevant chemical reactions, like, ones that are used to make fertilizer, for example. The problem is that, you need, I think in the 2016 estimate, the circuit depth was something like on the order of 1 million. Okay, so it's only 100 qubits, but they have to be ridiculously good qubits, and that clearly is not yet ready for the NISQ era. And I think that today people have managed to get things down to like depths in the thousands, but it's still too high, right? So, but I think that if we are going to get something that we can actually do in the NISQ era, without fault tolerance,
where, we will sort of see a speed up and can efficiently verify, and can verify that speed up in a natural way, then, simulating, quantum dynamics is probably the best bet that we know of. Okay, now we could try to take some inspiration from the black box world. Like we could look at Simon's problem, for example, which is, finding this sort of hidden shift. Yes.
Is there a reference for doing this kind of physics simulations for which the depth is only on the order of 1,000?
Let me say, just look at the latest stuff from the Microsoft group. Yeah, we can talk about it. I'll find. Or email me. I'll try to find that for you. Okay. So, interestingly, Simon's problem, we still don't know a concrete instantiation for it. Like we still don't know like an explicit hard instance of Simon's problem. If we had that, that might be an example of something that that would lead to a more a nearer term quantum speed up. And this has been an open problem for almost 30 years. I'm still very interested in the answer to that. Okay. Likewise, the correlation problem, which I introduced in 2009, with the goal of proving an oracle separation between BQP and the polynomial hierarchy. Okay, I was not able to do that. That was finally achieved 4 years ago by a breakthrough of Ron Raz and Avishai Tal. So they showed that this problem, you're given two Boolean functions. You have to decide whether one of them is correlated with the Fourier transform of the other one, right? So this problem is in BQP, but it is not in NP or even in PH, right? As an oracle problem. In fact, a PH machine sort of cannot distinguish, these two like correlated Boolean functions from completely random functions. Okay, but then now one could say, could we find some explicit instance of this problem? So are there any like explicit functions that would be given to you by circuits where one of them might be close to the Fourier transform of the other one, okay, but other than that they look random, right? And where you can't figure it out by just inspecting the circuits, right? But you could only figure it out by running the correlation algorithm on your quantum computer, right? Again, if we had that, then that might, I mean, it's an extremely simple quantum algorithm, so that that could lead to a NISQ speed up, but we just don't know how to instantiate the oracle by a real problem that would give you that. Okay, yeah, so that's the problem. Now, just a couple of months ago, Yamakawa and Zandry had a breakthrough. They gave a completely new exponential quantum speed up, and you're going to hear much more about that in the next talk, so I won't belabor it. But basically, they study the following problem: that you are given, let's say, a random or a pseudo-random function f, say mapping n bits to 1 bit, and now your task is to find a list of n-bit strings, let's say x1 up to xn, such that first of all, they all map to 0 under f. Okay, now that by itself is trivial, right? Half of all the inputs map to 0. So you just, pick a bunch of random ones. Okay, but then also when you take these n strings and you concatenate them, then you get a string of n squared bits, which is a code word of a specific error correcting code that you are given. Okay, and so, okay, this is a strange looking problem, but what they show about it is that it does have a polynomial time quantum algorithm, okay, for an appropriate choice of the error correcting code. Anyway, using the quantum Fourier transform and also convolution. Okay, you're gonna hear about it soon. Okay, but they also show that if f is just a random oracle, a random black box, then any classical algorithm that would find this preimage needs exponentially many queries to f. Okay, so so and finally, we can notice that this problem is an NP search problem, right? So if you find a solution, if you find, these pre-images that concatenated give you a code word, it is easy to check it, right? So it's an NP search problem. And this is the first time that we've seen an exponential quantum speedup for an NP search problem, which only requires a random oracle. Okay, there's no structure in the oracle that is necessary here. Unfortunately, there is still a lot of structure needed in the quantum algorithm. Okay, the quantum algorithm basically has to do a bunch of decoding of an error correcting code, on superpositions of inputs, which end up being lattice computations. Actually, yes, Greg.
Just a small question, just
Yeah.
to clarify.
Yeah.
NP search problem is identical, synonymous to FNP.
Yeah. Yes. Yes. Thank you. Yeah. It means a search problem where you can, efficiently verify an answer to it.
Well, sure, but
Yeah. But the important point here is not the decision. The decision problem is trivial. The answer is always yes. To is there a solution? The problem is to find the solution. So it's actually a TFN2, right?
so the code is chosen so that the answer is always yes.
Yeah, or at least it's yes with overwhelming probability over F. Yeah.
Decision problem by making it a little more complex.
Well, we don't know how to do that, and in fact, the Aaronson and Bias conjecture would say that you can't. I'll have that in a later slide. But
What goes wrong if you just say, look, for the following prefix,
Yes.
is there a solution with the following prefix?
well, because then it's not the same problem anymore. It's just not this. If you look at their algorithm, it will generate a random solution. It's not going to generate a solution with this specific prefix. Okay. So yeah. So although they eliminated all the structure from the oracle, the algorithm still looks kind of Shore-like. It still looks like something that we would have no idea how to implement in the near-term era. Okay, so then approach number 3 would be, well, start with these sampling-based quantum supremacy experiments, such as boson sampling, which Arkhipov and I introduced 11 years ago, and which has now been demonstrated by the team at USTC in China with about 100 photons. And actually, there's a new paper by Xanadu where they're, I still have to read it and see how much I, try to evaluate that. Okay, but the first quantum supremacy experiments were the ones from Google from late 2019. USTC has since also done random circuit sampling with 2D grids of superconducting qubits. This is what it looks like. This is the dilution fridge. As I said, the problem with all these things is that it takes exponential time to verify the results with a classical computer. For example, if you use this linear cross entropy benchmark. Okay, so I think an enormous challenge is to figure out how to take these near-term quantum supremacy experiments based on sampling problems and make them verifiable, make them efficiently verifiable. Okay, as I said, there are these very elegant protocols of Mahadev. And then, there's a sort of a more efficient version by, Kahanomoku Meyer et al. For specifically for quantum supremacy, right? But these all of these protocols for sort of verifying a quantum computation sort of require evaluating a trapdoor function on superpositions of inputs, which is sort of, which is again is kind of going to be a stumbling block in the NISQ era. So now a cruder idea would be, why can't we just take the, random circuit sampling type of experiments and modify them, to insert some kind of secret that, if you're just looking at the circuit, you won't know. but someone who, the person who generated the circuit will know the secret, and they'll be able to recognize the secret in the outputs that are sampled from that circuit. Okay, so what I would like is some protocol where a challenger creates a quantum circuit C that looks random, but it conceals some secret string S, let's say, such that we believe that you can only find S efficiently by running C on a quantum computer, right? And okay, now the question is, how do we implement this very simple idea? There was a very bold proposal, very early by Bremner and Shepard in 2008, but that was actually using some exotic error correcting codes. And their proposal was killed a few years ago by Kahanamoku Meyer. He gave a classical method for spoofing it. Greg, you had a question?
Is this slide, what I'm wondering about,
yeah,
is whether there's the advantage of Shor's algorithm,
yeah,
for instance,
yep,
as well as the correlation distance,
yep,
and the others, that there are actually theorems for conditional theorems, still theorems.
Yep.
There is a separation.
yep.
Whereas I don't know of any such theorems for this.
Yeah, I mean, of course, we will eagerly accept any theorems that we can get. Okay,
No,
but that might not be, that might be too much to hope for, because when we get the theorems, usually they are relative to an oracle. Usually they involve a black box.
They're going to have to, because you don't need
Okay.
P versus P, but
Right.
conditional theorems are okay.
Okay.
My question is,
Yeah.
is you're looking for NISQ and verifiable or
Yep.
NISQ and useful.
Yeah.
Okay. Is there any suggestion for NISQ and verifiable, and there is a conditional theorem that for the advantage?
That's exactly what I'm asking for in this slide.
This slide is as close as we can get.
That, yes, I'm asking for that. Okay, I'm asking for that.
Okay.
All right. I'm asking, do as much as you can in that direction. Yeah, all three. Yeah. So yeah, I literally had a slide with the inner, you came after this. This is what I want. Okay. So yeah, so we thought a lot about whether you can do this with boson sampling, whether you can design a linear optical network that will somehow look like just a random sequence of beam splitters, but that will secretly concentrate most of the amplitude onto a single output state. And Hui Wen and I were able to get a no-go theorem saying that, well, if you define the goal that strongly, then basically you can't do that with boson sampling. Okay, if you try to do it, it's going to, in boson sampling, the amplitudes are permanents of various submatrices of your unitary matrix. But if I try to concentrate a whole lot of amplitude on a single output, then it's permanent. Well, the permanent of that submatrix will have to be very, very large, and that will cause that matrix, that submatrix, to sort of stick out like a sore thumb. It'll have to be like the identity matrix or something, similar to it, so that you could just easily find it classically. Okay, that doesn't rule out that maybe there is some way to get such a protocol with boson sampling, but it would have to involve exponentially many different outputs rather than only one of them. Okay, so let me, I'm running out of time, but I want to give you as far as I know, a new open question, which I think is sort of directly relevant to this quest to design a sort of, to sort of take these, random circuit sampling quantum supremacy experiments and make them verifiable. All right, so given a quantum circuit C, let me call it peaked if well, really what I want to say is just if there is something about the, its output when you measure that you can easily recognize and easily tell apart from random. Okay, but just to be concrete, let me say if there is some basis state X that is observed with at least 10% probability when you make a measurement at the end. Okay, so if I pick a quantum circuit at random with overwhelming probability, it will not be peaked. Right, almost all of the outputs will have probability, on the order of 2 to the minus n, times various constants. Okay, and so this is only some very special quantum circuits that are like this. Okay, so now the question I ask is, suppose that I pick a random quantum circuit with say n qubits and n squared gates, but I pick it uniformly at random from only among the peaked circuits. Okay, then what does such a circuit look like? Okay, now one could imagine a boring possibility. Maybe what it looks like, one simple way to get a peaked circuit is you just apply a whole bunch of random gates, and then you apply the inverse of what you just did. Right, you just reverse everything to get back to the old zero state. Right, so maybe a random peaked circuit just looks like a bunch of gates along with their inverses, right? And then you would just start canceling them out, and you would trivially see that that the circuit does nearly nothing. Okay, but another possibility is that it would look obfuscated. So it would look to you just like it was a random circuit. Okay, and yet only by running it on a quantum computer would you see that it actually, is not random. It actually sort of creates this interference pattern that gives a particular output, state a large probability. Okay, so which situation is it? So a closely related question would be, yeah.
Easier to answer if you strengthen the first requirement to be just 1 instead of 0.1, like it's literally outputting a classical basis state.
That might well be easier. Yeah, but then it also may depend heavily on the gate set. Right. Yeah. So okay. So a closely related question would be: I give you an M gate random circuit. Now how many more gates do you need to tack on to the end of it in order to get a peaked circuit? Okay, so from recent results on T designs, we can show that the answer must be at least M to some power. Like it must be at least M to the 1/10th power or something like that, right? From like results of Brandau and Harrow and so forth about random circuits giving you T designs. Okay, we also know that the answer is at most M. Why? Because you could always just invert the circuit, right? And right, just like this, and get back to a peaked circuit. Okay, but it actually matters a lot where we are between these two. Okay, like if there's any improvement over M, right, then this says that the output of a random circuit actually has some kind of pattern that you can non-trivially access, right? And if you could then just figure out how to generate that, then that would give you a candidate for a NISQ quantum supremacy experiment. Okay. You would say, apply this random circuit and then tack this extra stuff on the end of it that tells, that makes it peaked, right? And then, so yeah, so, or more generally, we could ask, is there a fast way to sample peaked circuits, in such a way that they are polynomial time indistinguishable from random quantum circuits? Okay, and sort of you could say any such way would constitute a candidate for NISQ quantum supremacy experiments, right? It'll be NISQ because the circuits look random. It will be verifiable because the circuits will be peaked. Okay, so so I would like to know whether this is possible or not.
Sorry, I'm missing something because you just run it multiple times and distinguish by the.
Oh yeah. I mean polynomial time classically indistinguishable.
Oh, okay.
Yes.
Okay.
Yeah. That's the entire point here, right? So yeah. So one can also think about this in Michael Nielsen's sort of geometric framework for circuit complexity, where you think of a quantum circuit as like a geodesic, in some manifold. And what a peaked circuit corresponds to is it's some kind of short path which starts at a computational basis state, wanders around in this huge space, this SU of 2 to the n, and then ends up close to another computational basis state. And then the question becomes sort of how do we find paths, short paths, so polynomial sized circuits, but that are exponentially hard to sort of contract to trivial paths, which sort of would never leave the computational basis. Right, it's it has a topology where like every path can be contracted, but we want a path that would be exponentially hard to see that it can be contracted, right? So you sort of wander out into the vastness of Hilbert space, and then you come back to the computational basis, right? But in some way that is more interesting than you just go out and then you just turn around and return exactly the way you started, right? You want to sort of go around some roundabout way where it's hard for a classical computer to see what's going on. Okay, so I had a whole second part about the black box quantum speedups, which I'm going to, in the collision problem and so forth, which I'm going to skip because I'm out of time. And then sort of a hierarchy of structure in black box problems. And then this Aaronson unbiased conjecture, which is related to what Umesh asked about before. The Aaronson unbiased conjecture basically says that for decision problems, there should be no exponential quantum speedups relative to a random oracle. Okay, and there's been some very exciting recent progress toward proving that conjecture by Bansal Sinha and Ronald DeWolf. And we sort of interpreted this as sort of saying, well, relative to a random oracle, you can only ever get a Grover type of quantum speedup, right, and not an exponential one. But that interpretation is too strong, as we now know from Yamakawa and Zandry, okay, which you're going to hear about very soon. So I think this is deep in the mystery of the role of structure in quantum speedups by saying that you can remove all the structure from the oracle for an NP search problem, by putting the structure into the algorithm. So my concluding thought, is there a law of conservation of weirdness? That, for every exponential quantum speedup, there must be some weirdness in the problem statement that you exploit to focus amplitude on the rare right answers. How small can we squeeze that weirdness, and can we squeeze it into a NISQ device? So that was all. So thank you.
Already about the questions, maybe if there's any question.
Clarify the status of the conjecture with respect to the new result.
Yeah. So that was just, sorry, what I was trying to say before. But so the key point is this: the Aaronson unbiased conjecture, as far as we know, is still true. Okay, in fact, it's even assumed in the Yamakawa-Zandry paper to prove one of their subsidiary results. Okay, the key point is that this conjecture is for decision problems, right? Yamakawa and Zandry are studying an NP search problem, right? So it's just not covered by this theorem, right? So you might think the difference between decision and search problems is not that big a deal. This, we're now learning that it's a huge deal.
Maybe we can do the question. Okay, unless there's something.
It's short. For your open question.
Yes.
Would you still consider it to be verifiable if the circuit is sampled by a quantum computer?
Well, I mean, that would still be interesting. Like, it's even interesting if you just need brute force, if you need exponential time to generate the circuit, right? That's already interesting to me. As in, already I don't know how to do it. Okay, but now if you could do it with a quantum computer, so much the better. But then we would still have work to do to get something practical. That we can do it in the right to do something in the NISQ era. I want a classical algorithm to generate the circuit.
Great. So we'll take a break until the next talk at 10:30. So